is on the fundamental theorem of calculus, which is a kind of lengthy topic. It's a very important topic that serve as a link between the derivative and the area, right? So before I begin on this topic, let me just revise with you what we have studied so far. So far, what we have done is that we have learned how to perform an derivative. If you have a function of fx, capital F, then when you differentiate it, then you get back another function. So in this case, we say that I will say fx is an antiderivative for fx. Okay, so we have to revise the idea of antiderivative. So in this case, when you have a function f, this function capital F is said to be the antiderivative to the small function f. That is, when you operate on the df, when you operate on the capital function f with an operation of d dx, then you get fx. So you can actually get back from fx to capital function f by carrying out an reverse operation. I use this symbol to represent an inverse operation. This inverse operation is an operation that is going to return small f to fx. So the inverse operation will act on the small f to give you back fx. So anyway, when you have such a relationships, then we said the capital function f is then antiderivative to the small function f. So if a capital fx is an antiderivative to the small function f, then we would say again that the collection, if capital function f is an antiderivative to the small function f, then any antiderivative of capital function f add with any constant will still be an antiderivative to the small function fx. So we called the collections of all the antiderivative capital function f a symbol. So we define a symbol for the antiderivative. So the symbol for the collections of all the antiderivative is represented by a symbol with an integral sign. And the integral sign will emit the small function fx. So this is an symbol or a mathematical notation that represents the antiderivative of the small function fx. The antiderivative for the small function fx is written in this form. That is, you have a indefinite integral sign, and you put in the small function fx. That will represent the collections of all the antiderivative to the small function fx. So the antiderivative of the small function f is fx. So try to understand the definition of antiderivative. The discussions on antiderivative has been recorded in previous lecture already. Okay, so I'm just repeating here that there exists a definitions of the antiderivative. So you are given some function f, then you should understand what you mean by the antiderivative to the small function fx. So that is what I want to tell you. So the other thing that we have been talking about since the last few lecture is another idea of the remnant sum. Right? So remnant sum that has been discussed in the just last topic, it's the function fx that is to be integrated for the variable from a lower limit to some upper limit, right? So this will represent the integrations of the small function fx, and it gives you the area of a functions that is bounded between a and b, and this is supposed to be a continuous function, right? So this is a function y equals to fx. So the area that is represented here is the calculated using the remnant sum. So you calculate the remnant sum of ck delta xk, then you sum from 1 to infinity. So this remnant sum, when it converges, it will give you the area of the function, and we represent the converged values of the remnant sum by this symbol, which represents the area of the function integrated from a to b. Such a function, if it's continuous, then it must be integrable. A function that is said to be integrable, it means the remnant sum of it exists when x is taken the limit from a to b. So here we are talking about the integrations of the function, which represent the area of the function. So this is about the integration, right? So integration. So integrations of a functions, it's represented by this symbol. It is a symbol that represents a number, right? It is a number which is just the limit of the remnant sum. Whereas in the previous case of the antiderivative, the collections of all the antiderivative is represented by a symbol of an indefinite integration or indefinite integral. So this symbol that is written here is a symbol that represents the antiderivative, and this symbol is called the indefinite integral. Okay, it's called indefinite integral. Whereas when we talk about the area of a functions, which is the remnant sum, then the area is represented by the integration symbol, which looks like this, where it has a lower limit to an upper limit. So this symbol, which has an integration with a limit from a to b, is called an definite integral. So the confusing thing here is that the indefinite integral and the definite integral looks almost the same. It is purposely designed, the symbol of both integral is purposely designed to look alike, but they are actually different things, right? So for definite integrals, what you have is a symbol that is like this, and then you have a container, then you have a dx. So inside here you have a function. So this indefinite integral represents the antiderivative, whereas for definite integrals, the symbol of it is you have a container where you put in the functions, and then you also have a limit, right? And this whole thing, which is the definite integral symbol, represents the remnant sum of the function from a to b, and it is a number. This is the symbol called indefinite integral that represents a collection of the antiderivative function. So the indefinite integral is a function, whereas the definite integrals is a number. Okay, so these are two totally different things. So when you take a look at take a step back and look at the two symbols, the indefinite integrals and definite integrals. These are two totally different things. Convince yourself these are two totally different things. One is a collection of function, which is the antiderivative. The other one is the area under the graph. Right? So these two are to be connected through the topic which we are going to talk about, the fundamental of calculus. So basically, the fundamental of calculus would tells you how to relate these two aspects, how to relate the definite integrals and the indefinite integrals. So you think about it, it's actually quite an important steps forwards, because first we learned the antiderivative, which is just a concept that is related to the derivations or the differentiation. Then in topic 5, we learned about area or the Riemann sum, which is just calculate the area under the function. So the area under the function and the derivative, what are the relationships? The relationship is provided by this fundamental theorem of calculus. Okay, so in order to prove the relationship between the definite integrals and the indefinite integral, we have to first mention a theorem which is called the mean value theorem for definite integrals. So again, definite integrals is a symbol that is represented by this. This is a definite integral that represents the area of a function from A to B. Okay, so if you have gone through my lecture during the flip class, the last part of the lecture yesterday, we talked about the idea of the average of a function. So if you have a function that is defined continuously between A and B, such as like this, then you can try to calculate the area under the graph. So the area under the graph is just given by this, given by the definite integral of the function y equals to fx. Okay, so that represents this function, and then this sketch area represents the area that is represented by the definite integration. So we define an average for the function. The average of the function is defined to be a number. Let me change my color to say a green color. The average of the functions, which we call this f bar, is thought to be a number such that the area under the curve of the function area. So the area of this sketch sheet is just given by the height of the f bar, because f bar is supposed to be a constant. So you multiply the f bar, which is the height, with the width, which is b minus a, is defined to be equals to the area. If you can find a number of f which represent the area, represents the average of the area for the function fx from A to B, then this would be showing you estimates that describes the average values of the function. Right? So the average of the function is simply equals to the f of fx integrated from A to B, which represent the area, divided by the width, of the area. So the width of the area is this. So you replace, in this sense, replace the area of the function by a rectangle which has a height that is equals to f bar. So this is the idea of the average. And yesterday also we mentioned that if you have a function that is continuous, if the function that is continuous between A and B, then for sure you would be able to find a values of C that is lying between A and B, such that the value defined at FC, so this is the values of FC, such that the values of FC wait, I think this is not what we was talking about yesterday. Now, I think yesterday what we was talking about is not this. This is to be discussed in this lecture, not in yesterday's lecture. So let me repeat myself again. What I want to tell you is that according to the previous topic, it is said that if you have a function that is continuously defined between a and b, you have a function fx that is continuous, then if fx is continuous, then the theorems guarantee that fx is integrable, right? So when you say fx is integrable between a and b, it means the remnant sum. It means the remnant sum for the functions between a and b exists, and the invariant, the remnant sum converge to a number. So if this number exists, then we say the functions is integrable. Not all functions are integrable, but the theorems guarantee that as long as the function is continuous, then the function must be integrable. Okay, so remember these very important statements. Continuous function is integrable. Okay, so then once you understand the idea of the average of a function, and the other thing that is the continuous functions is integrable, then the theorem 3 says that any function that is integrable, for any function that is integrable, you can always find a values. You can always find a values of c that is lying between a and b, including a and b itself, such that at the values of c, the values of the function at c represents the average of the function. Right? So you understand what you mean by the average of a function. Average of a function is a number such that the area of the average, which is a constant times the width, is equals to the area of the integrations. Okay, so the theorems that we talk about, I think theorem 4 says that there must always exist a values of c such that fc is the average value. That is, you can always find a values of c at which the height of function fc represents the average of the function. So in other words, if you have an average of the functions that is guaranteed to exist, then you can imagine it to be like this kind of situations. This represents the area under the curve of the functions. Then use green color to represent the average. Say for example here, this is a values of c, this is a, this is b. C is a number that is guaranteed to exist, at which the values of c of the function at this point define an area that is of this, right? So the green box that I write down here represent the area defined by fc. So the area of the green box is fc times b minus a, and this is supposed guaranteed to be equals to the area of the functions between a and b. So okay, I said again, I think something is wrong with my, so I have to share again the screen. So wait for a while so that I can go back to the share screen. To that we are talking about, the theorem guarantee the existence of a values of c such that fc is just equals to the area divided by the width of the function. So that is what this theorem is about. Okay, so it's a theorem that guarantee the existence of C, where f at C represents the average of the area, the average of the function for f lying between f line between A and B. Now this is very important. Well, it's important is because it would actually give you a theorem that would relate the definite integrals and the indefinite integral. Now later on, we will be seeing that if you have a function that is defined between A and B, then you can always guarantee an existence of C where the values of C for the function fx multiplied with b minus a is always equals to fx integrated from a to b. Right? So if this is not b, but say a plus some small values of delta, then the same functions the same relationship will also hold true. So no matter how small the width of this is, there is always guarantee to have a values of C that is sandwiched between the left limit and the right limit. So we need this theorem in order to help us to relate the definite integrals and the indefinite integrals. Okay, so that is what I want to tell you. We need to have theorem 3 before we can prove the fundamental theorems of calculus. This is an example, figure 5.17. It is not showing on the screen. It's supposed to show you the, okay, I think this is what I want to show you. Okay, so this is a counter example that shows that if you have a function that is not continuous, then you are not guaranteed by this theorem 3. Theorem 3 says if the function is continuous, then there is always a C that is sandwiched between A and B, where the functions at C represents the average of the function. And basically at C, FC times the width of the B minus A represents the area under the curve. But if you look at this counter example, this is obviously an discontinuous functions. So you ask yourself if it is possible to have a value of C that represents the average of the function or not. So the average of the function is easily understood, right? So the average of the function, as I mentioned, could be easily calculated, right? So how do you calculate the average of the function? Average of the functions is easily calculated to be just equals to the integrations of the functions. Well, not necessary, so maybe I shouldn't say that. So you look at these functions which is not defined, and you ask yourself what is the area of the function from 0 to 2. And obviously the functions roughly, if you want to evaluate the area, it should be just equals to the width, which is 1 times the height, which is 1. So the area is equals to 1, right? So by looking at the geometry, the area for this discontinuous function from 0 to 2 is 1. But in this case, can you find the values of C that is lying between 0 and 2 such that the function evaluated at C is equals to 1? Can you find such a values of C in the intervals of 0 and 2, where the function f at this point C is equals to 1? So obviously you can't, because sorry, I think you can or you can't. I think this is yes, I think in this case, if you ask these questions, there's obviously a values of C where, okay, so I think, I'm sorry, the average of the functions for this area is actually not 1, but it's actually half, okay? The average functions area is 1. Okay, sorry, now I have to redefine my questions. Now the area of the function is indeed equals to 1, but the average of the functions, let me redefine my questions again. So we know the area of the function is 1, and you ask the very simple questions, what is the average of the function? So the average of the functions is equals to half. The average of the function is equal to half. Why is that half? Because by definitions, the average of the function multiplied with the width of the b minus a. So a is 0, b is 2. So the area defined by the average of the function, which is this one, should be just the f bar times 2 minus 0. So this defines the area of the average for x between 0 and 2, and the definition requires the area of f bar equals to the area of the function from 0 to 2, and the area from 0 to 2 is equals to 1. So here the average of the function is supposed to be half. So can you find a values of c that is lying between 0 and 2 such that the values f evaluated at c is equals to half? So if you look at the functions here, is there any value of c where the function is equals to half? The answer is no. The reason is because the function is only defined. The function is only defined to be either 0 or 1, right? So the function f that is shown here is a piecewise function that is either 0 or 1, right? That is, for x which is larger than 2, the function is larger than 1, the function is 1. When x is less or equals than 1, the function is 0. So the fx takes on only 0 and 1, but it would never able to be equals to half. In other words, you cannot find any values of c where the function at c is equals to the average. So in this example, we ask the question, what is the average? Yes, the average of the function is defined. It is half. But can you find a values of c in the domain of this function where the function f at c equals to the average? The answer is no, right? But this is actually a consistent result with the theorem 3. Theorem 3 says if you have a function that is continuous, then guarantee the existence of c. But here it's a function that is not continuous. Therefore, you do not have the existence of c. The existence of c is not guaranteed. So it's a counterexample that illustrates the applications of the theorem number 4 here. Okay, it's just illustrations that guarantee the existence of the values of c. Only apply for function that is continuous. So I hope that until this stage you start to appreciate the usefulness of the continuity, right? So if you have a function that is continuous, everything is nice. It is integrable and it guaranteed existence of c where f is defined at c to be equal to the average. So we love continuous function. Function that is discontinuous sometimes give rise to a lot of problems. Okay, so this is another example. One, it is just another example. It's not coming out. I don't know why. I think it's very slow. Okay, so this is an example that says you have functions of one. It's a function that is given by 4 minus x, then you can easily calculate the area of the triangle. So the area of the triangle is just equals to half times the height, which is 4, times the base, which is also 4, so which is just equals to 8, right? So the area has an values of 8, which is the area of the function defined to be between 0 to 4. Then can you find me the average of the function? The average of the function could be easily found to be just equals to the average, which is what we want, times the width of the functions. The width of the function is 4 minus 0. And it's supposed to be equals to a, which is 8. Right? So from here, it is easily understood that the average for the function 4 minus x between 0 to 4 is just simply equals to 8 divided by 4, which is 2. So now I have shown to you that the average of the function here is 2. So can you find me a values of c that is lying between 0 and 4 such that function evaluated as c is equals to the average. Here is supposed to be f at c is equals to the average of the function, which is 4. Okay, so the answer is very simple. C, if chosen to be 3 over 2, then the function at 3 over 2 is just equals to the average of the functions, which is equals to 2. So this is just a very simple question, right? I think last time in the exam we have the same questions again. I give you a functions that is defined between some domain from A to B, and ask you to find what is the corresponding values of c such that f as c equals to the average of the function. So it could be quite easily answered. So it's just an example that illustrates the use of the theorem 3. Okay, this is theorem 3. Okay, so theorem 2 usually requires you to answer the questions of what is the values of c, where the function of c is equal to the average of the function. Right? So now we are almost there to talk about the relationships between the definite integrals and indefinite integral. The first part, so the fundamental term of calculus is divided into two parts. The first part is to establish the a new functions called capital F that will shown to be the antiderivative of a small function f. So we want to first talk about theorem part 1, the fundamental theorem part 1. After we mention theorem part 1, then you would be then go to the theorem part 2. So theorem part 2 is the continuations from the part 1. So we have to talk about part 1 first. Basically, we want to prove that if you have a function which you define as form that is in the integral form, a function that is defined to be integral form, then you establish that the derivative of the capital function f is a small function f. That is, f capital function fx is an antiderivative to or for the small function fx. Right? So the function that we define here is the capital function f. Okay, so this is essentially the first part of the fundamental theorem of calculus, which we are going to talk about here. So first of all, you just think of a new function, which is fx. So imagine you have a function. Maybe I should write this with another piece of blank color. So imagine you have a functions which is ft, right? A function which is, sorry, a small function ft. small function ft, which is defined to be on the t-axis horizontally, and you have a function of f of t. Okay, then the f of t starts from some initial value a, and then it ends up to be some values on the other side, which is b. But instead of calling this b, I'll call this x. The x is the upper limit of the function ft, which I'm going to integrate. So imagine I integrate the function small ft, and then I form the definite integrations of the function from a to x. So what would this represent? This would actually represent the area of the functions ft between x equals to a to x equals to x. But here I'm not using x as my name for the variable, but the independent variable here is called t. So try not to be confused, okay? That is, I have a function f expressed in the variable of t, then I integrate f of t from a to x, where x here is just a variable. You can imagine that x is a slider where I can slide the x from 0 to infinity, right? So when I slide the values of x, then x will change, right? So x change from anywhere from a to infinity, right? So when I slide, I'll change the x to become larger or smaller, closer or further away from a, then the area defined under the continuous function ft will also change. So I can represent the area of this shaded area of ft as a function of fx. So this capital Fx represents the area of the function ft ranging from a to x. So here x is an independent variable which I can slide independently. Then the area of the function ft would then depend on the values of xx. So that is how I come up with this function f, capital function f. So there's a function, small function f, and capital function f. So make sure that you make a distinction between them. When I mention this f, I would always try my best to explicitly say it out, whether I'm referring to the capital F or the small letter f. So here I'm defining a small as capital letter f to represent the area of the small function f for t ranging from a to x. So just a definitions of the functions. That's all I want to say. So wait, I always get this thing mistakenly done. So no harm. So let me go back. Now, once I have defined my small function f and big function ft, then I'll go to the next. Now, when I go to the next, I'm going to show you that the capital function ft, is actually the antiderivative to the small function ft. So the next thing I'm going to talk about is to show you that indeed the capital function f is indeed an antiderivative to the small function f. Now the idea is actually quite simple. What you do is that you start to define the function of capital function f, which we already done. Then you construct the difference between the capital function f at x plus h, where h is a small increment in the values of t, right? So here we stop at x when you integrate the area of small function f from a to x. Then you can also integrate the function of small function f from a to x plus h. So this represents the area of the small function f from a to x plus h. Then fx represents the area of the small function f from a to x. Then you take the difference. So the difference is actually represented by this shape. Right? So this is a shape that is represented by the difference between capital function f at x plus h minus capital function f. Right? So definition-wise, the difference between them is then just given to be the area of the small function f integrated from x to x plus h. So this is just the area of this small strip, which could be very small if you take h to be infinitely small. Okay, so h is not a value which is 0, but it's a very small positive value. So this is the relationships that could be quite easily understood, that the difference between the f, capital function f, is just equals to the area of the small function f that is represented by these strips. And then when you make some small rearrangement, then you can show that the difference of the f function divided by h is just equals to the integrations of ft divided by the same factor of h. Right? So what you do is just you divide this by h, then you get these relationships. Now what this relationship says is that you have an f of t integrated from x to x plus a, right? So not x plus a, but x plus h. So this is h, not a. And this is guaranteed to be equals to a values of c multiplied, yeah, I think multiplied by the width of the values of c. So you have a h here. So this statement is a statement. This is a statement that is guaranteed to be true by theorem 3. The theorem we have just discussed a minute ago. So a c is a value that is guaranteed to exist between x and x plus h, where the values of the c that is lying somewhere in the middle or somewhere between x and x plus h, you don't care where it is, but it is guaranteed to exist, and its value is limited to be sandwiched between x and x plus h. So you must guarantee the existence of such a c where the values of f at c represents the average of the function within this small region, right? So you guarantee an existence of c here. So finally, you get these relationships that is saying that the values of the functions, that is this expression, must equals to a values of f defined as c. So here c is a number again that is sandwiched between x plus h and x. Then you take the limit of h going to be very small. You make h to be as small as possible so that the width of this strip become more and more narrow until it almost touched each other but never quite touched each other. So this represents the limit of the functions, the limit of the difference between the two functions divided by h, with h going to be 0. Then that, by definitions, is the derivative of the capital function fx. So when you equate left to right, what you are showing here is that you are applying the definitions of the differentiation, right? The derivative of the capital function f is defined to be like this. So here we are applying the definitions of derivative for capital function f, and then the right hand side here is actually f of c, right? But in the limit when h goes to 0, c, which is sandwiched between x and x plus h, would then tend towards x, right? Because it is sandwiched between x and x plus h, and h is getting closer and closer. So in the limit when h almost become 0, then the values of c would just approach x in the limit of h goes to 0. So finally, fc would then converge to the values of fx. So finally, what we are going to show here is simply the fact that so maybe I write it here. It's simply saying that the limit of f of x plus h minus f of x divided by h when h goes to 0 is just equals to the f prime of x, and this is just equals to f of c, where c is limited to be this plus h, and when h goes to 0, then c would then just tends to x in the limit h goes to 0. So we just established this fact, that is f prime is just equals to the small function f. That is how we come to this very simple conclusion, that capital function f is an antiderivative to the small function f. So so we'll skip this this slide, so you can read it yourself. So that is the fundamental theorem of calculus. That is to say, if you have a function that is a small function f, when you integrate it from some constant, where this constant is arbitrary, it doesn't care what values of a is, it's just any number, and then its upper limit is an independent variable, then this would define a new function called the capital F. So the capital function F is constructed from the small function f. Give me a small function f, you integrate it from a to x, that will define a new function which you call the capital function f. And the theorem 4 says that if you construct such a function, fx is simply the derivative, the antiderivative for the small function f. Right? So this is the first thing. So try to understand the idea, right? So start with small f, then you define a capital function f. Then the capital function f is the antiderivative to the small function f. So this forms the first part of the fundamental theorems of calculus. So so just convince yourself that once you define such an function fx, then the fx, capital function fx, is just the antiderivative of small function fx. So you would write these statements, that is, the capital function fx plus any arbitrary constants is the collections of all the antiderivative to the small function fx. So you write this symbol, that is, the collections of all the antiderivative is just equals to the indefinite integral of fx. Okay. Then this is just a symbol, right? I mentioned this earlier in this lecture. The indefinite integral symbol is not an integration. It is an indefinite integral symbol that represents the collections of all the antiderivative to the small function fx. And at the same time, the small function fx is the derivative of the capital function fx, right? So these are the relationship that relates capital function f and the small function f, and their relationship could be understood from this slide, right? So you have a small function f on the right and the capital function f on the left. Then the function of capital function f and small function f, they would be related to each other through the derivative and the antiderivative operation. So upstairs, d dx is the derivative. The downstairs indefinite integral of f dx is the inverse to the derivative operation. The antiderivative operations is just the inverse of the d dx. Okay, so I think I mentioned this earlier on also in the previous lecture. Okay, so you have these very simple relationships. The use of the theorem 4 is that once you have defined the functions of capital function fx, then the derivative of the capital function fx, it's waiting to be shown. I don't know why it's not showing correctly. Okay, I'm showing you this. Yeah. So the main use of theorem 4 is that you define a capital function fx. You define a capital function fx and you differentiate it, it gives you the small function fx. Okay, so let us look at a simple example of this. You are asked to find the derivations of this function. So this is a function of f. So this is a small function. This is a function of capital function f in the variable of x, where the x appears to be the variable that goes into the definitions of a definite integral, right? So the upper limit of the definite integral cos t dt from a to x is the integral functions that define fx. So let me repeat again. The capital function fx is defined to be an integral functions of another function, which is cos t. Right? So you integrate cos t from a to x, that define an integral. Right? Define an integral. Therefore, the function that is defined by this integral is said to be the integral function, right? A function in the forms of an integral. But this is to be differential. This is to be different from the other function that we are used to, right? In previously, for example, when I say I give a function which is always say either a cos x or say x squared plus 2, right? So this is just a usual way of defining a function which you are familiar with. But now we are defining a function which is not so direct, but the function capital F here is defined through an integration. So get used to this kind of a new way of defining a function. So any variable that change that causes a values of the function to change is a function. So here capital functions depend on x, and when x change, the values of capital function f change, then capital function f is a valid function. Okay, and it's a continuous function as well because the cos t here is a continuous. Okay, so just convince yourself that you can that this is a wait okay, so again I got stuck with my with my iPad for some reasons. So let me do it again. Okay, so I've already resumed my recording. Let us look at the example 3. Okay, so this is what I'm going to do. So I'm going to do expressions 1. A, I'll call this function fx to be defined as an integral function. So the integral function has the form of ft dt integrate from some constant to x. Here, in this case, my ft for part A is just a function of cos t, right? It's a function of cos t. So if you have a function f, capital F, defined in terms of the integral function of small f, Then theorem part 1 of the fundamental theorem of calculus says that the derivative of the capital function f is just equals to the small function f. Here, the small function f, when you integrate it, you integrate in the variables of t. But when you take the derivative of the capital function f, then it returns the original, the small functions in terms of x. So this is just guaranteed by the theorem. You just can use it as it is. So then you don't need to do anything. It just shows that the derivative of fx, which is just dx of the function of some constant a to x cos t dt, you don't really need to do any calculation. You just apply straightforwardly the fundamental theorem of calculus part 1, you get the answer to be just cos x, right? So the fact that the derivative of this thing, the derivative of the integral function is equal to cos x is just guaranteed by the fundamental theorem of calculus. It is, of course, it's a formula, but it's proven through the very rigorous definitions of limit and the area of the function, small function f, as we shown in the previous slide. Of course, operational wise, there's not much difference, right, when you apply the formula, but it would be good if you understand that when you apply the formula does not come from nowhere. It comes from some fundamental and rigorous definitions and derivations as well. Okay, so we have done with the first part of the questions. Then maybe just look at the other part of the questions. The other part of the questions is this. So you have another function which is also of the similar form. So the answer to this is according to the fundamental theorem of calculus, f, which is defined as small ft dt from some a to some x, is just equals, this would just simply means the derivative of it is just equals to the small function f of x. Right? So by looking at part B, the answer is simply equals to 1 over 1 plus x squared. That's all. That's the answer. Right. So similarly to this part of the questions, now for the fundamental theorem of calculus, the lower limit is a constant and the variable of x appears in the upper limit. So this function is not defined properly in terms of the limits. So you have to revert the limit, and when you revert the limit, you are applying the one of the rules that we mentioned in earlier chapter, when you have a functions where you have a and b for some kind of fx. When you swap the upper limit and lower limit, for b become a become b. So when you swap them, or you permute a with b, then you would introduce a sign of a minus sign. This is just a definition, okay? That is when you integrate from a to b, you got positive. When you integrate from b to a, you are going in the opposite directions. Therefore, you introduce a minus sign. So this is according to definition. So this is just simply equal, the y is then just simply equals to a constant. 5 is a constant, right? Then you have x, and then you have a sine t over dt. Therefore, when you integrate, let me round off this one first. So when you integrate y, then the derivative of it is simply equals to y prime is then just simply equals to the negative of 3x sine x. That's all. The answer for part C is just equals to 3x sine x. Now, the part D is slightly more complicated. You are not integrating the functions from a constant to x, but you integrate from a constant to another functions, which is x squared. So if you have a limit of x, then the applications of the fundamental theorem part 1 could be just applied straightforwardly. You don't even need to calculate, just copy the expressions of the integrand function and just change your variable from t to x. That's all. But in the case where the limit or upper limit is a function of x instead of just x itself, then you have to do some additional work. So this is what we are going to do here. You have to integrate the functions of up to x squared. So you are not integrating it as x but x squared. So I'm just rewriting these questions, part D, in a more explicit form. Then you just use chain rule. You just rewrite the function fx, that is the function that you want to differentiate, capital function fx, into an what we call composite function. So you define u to be x squared, then you define a small function f to be just equals to cos t dt, integrate from 1 to u, right? So this is just a very simple, straightforward, what we call rewriting the functions to be integrated, the function to be differentiated into the forms of a composite function. We have done this very often in the previous exercise. You have some complicated functions, you look at the function, then you decompose it into two smaller functions, u and f, and you compose them to represent the original functions. Then you apply the chain rule. So applying the chain rule requires you to be able to recognize the original function as a composite of two independent functions. And usually the decompositions of a complicated function into a composite function is kind of straightforward and not very complicated. So you learn how to do that, and I've shown you many examples. Here is one of it. Once you define your u to be x squared and f of u to be the integration of cos t from a constant to u, then straightforwardly you will be able to see that the functions capital F that you want to differentiate could be then just decomposed into f composed of u. Then you apply the chain rule that says that the d dx of f composed of u is just df du times du dx. Then so d du of fu is just d du of 1 d du of the integrations of 1 to u with cos t, right? So here this result can be just simply obtained to be just equals to cos u according to the fundamental term of calculus part 1. d du of integral functions where it has the same variable could be just straightforwardly evaluated, right? You just copy the integrand. Here the integrand is the cos of t. So fundamental term of calculus says that the derivative of this integral function is just cos u, and here you have d dx of u, and u is x squared. You put everything in, then this will give you the function. Okay, the answer is actually quite straightforward. So we have finished discussing part D. Then have another example which could be quite complicated. It is a question that is asking you to find a function called fx, small function fx. Okay, this is a small function fx that is asked by the question. You are asked to show what the function of fx is. I'm waiting for the screen to display my page. Something is not going well. Okay, so here you are asked to find what is the form of the function, and this function has a name called small f, and is defined to be between -90 to +90, and you are given a clue. You are given two clues, right? So you are asked to find this function. This function has to fulfill two conditions. That is, the values of the function at 3 must be 5, and the derivative of the function must be tangent x. Right? So how do you find the answer? So again, the answer could be easily found from the fundamental term of calculus. So fundamental term of calculus says that if you have a function that is d dx of fx, it will give you ft, and ft is a known function if fx is defined to be a function of ft integrated from some constant to x, right? So the relationship between capital F and small f, if they are related, then the derivative of the capital F will give you the small function fx. So here you are saying that you are asked for some function f, where when you derive it or when you take the derivative of it, it gives you tangent. So obviously you can first write down an integral function which you name it capital function fx that is related to the integrand in the definite integral to be like this, right? So when you want to get a function of y such that the derivative of it gives you tangent x, then straightforwardly, you know, okay, let me define a capital function f that is related to tangent t through this form. Why is that so? Because if the capital function f is related to tangent t through this integral form, then the derivative of the capital function f will give you tangent t. So this will fulfill this condition. So your tangent, so your capital function f would then fulfill one of the conditions that the derivative of it is equals to tangent t. So this will give you the first part of the answer. That is, if you define fx to be integrations of tangent t from a to x, then derivative of it will just fulfill tangent x. So you get the first part of the answer correct. But how do you get the second conditions to be fulfilled? The second condition is that the functions of f, which is not yet found, has to fulfill the condition that when x equals to 3, the value of it is 5. So if you define your f to be a tangent, then you have to also find out what is the values of a, such that the functions of f at 3 is equals to 5. So if you define your function f to be just like this, you have not actually found the answer yet. You have only found the first condition fulfilled, that is dy dx of capital F is tangent x, but you have not been able to fulfill this condition. So you have to construct a function of fx from the capital function f. So the capital function fx is not your ultimate answer, but it is an answer that has to be further tuned in order for your answer to fulfill the conditions. This is actually a what we call a boundary conditions, you want to say, and you want to name it, it's a boundary conditions. It is a condition that contains some arbitrary constant, and you have to find the arbitrary constant's value in order for the functions to fulfill this condition. Okay, so once you have get the capital function f done, then you just look at the thing slightly closer. So if f is defined to be in the form of tangent t dt from some constant to x, then you can form what we call an integral, right? So you can form a new functions which is from which is built from capital function f. So let me go to the next slide. I think the next slide explains a little bit here. So you have to construct the desired functions of fx using the capital function f that has to fulfill these conditions. So one way to construct the desired function small f from fx is obviously this, right? So you just have to add a constant to the capital function fx. Now, why is it so? Remember, if fx is an antiderivative to fx, then any sum of the fx to a constant is also an antiderivative. So the collections of all the antiderivative is still the antiderivative, right? So you write down the most common form of antiderivative, which is capital function f plus a constant. Now let me say that again. If fx is known to be the antiderivative to fx, then any constant added to the capital function f is still the is still the antiderivative to the small function fx. Okay, so with this in mind, then fx is just equals to the small function fx is just equals to the capital function f plus a constant. So this is the function that may allows you to fulfill the condition that f of 3 is equals to 5, right? So here you have a capital function f where you have a constant which you do not know what it is, and you have another constant also you do not know what it is. But you can easily get the constant a and this constant here by slotting in this value. Okay, so the simplest way to find what values of a and the constant in your case, in your small function f, is easy, right? You have to think, what should you choose for your a value and the constant so that the small f at 3 is equal to 5. So obviously, one simple way is to choose your a to be just equals to be what? I think you can choose your a to be any number. Just choose it to be any number because it would not change the output. So you can just choose your a to be 0. Right, so you choose a to be 0 as long as it's a constant. That it doesn't matter what the values of a is. So you also have to fulfill the condition that f at x at 3, the function of f is 0. So how do you do that? Just simply look at this one. Then you demand that f at 3 is equals to 5. So you just impose this so-called boundary condition into this expression by setting a equals to 0. So in that case, you slot in a equals to 0 and f at 3 equals to 5 into these functions. You'll be able to find out what the constant is. It's very simple. F at 3 is just equals to 0 to x tangent t t. So here sorry, I think I made a mistake. I should not set a equals to 0. I should not. If I set x, if I set a equals to 0, then I got into trouble. Now why is that into trouble? Let me explain to you. So I'm slotting in x equals to 3 into the function small function f. Here x represents 3, so this would be a 3, right? Then add with a constant. So this has to be equals to 5. So now I have a very simple relationships which I have to rewrite because my writing is just terrible. So f at 3, f at 3, maybe I should go back to the previous slide. Yeah. Yeah. So f at 3 is f at 3. Oh, this one. F at 3 is just equals to just now I choose it to be 0, right? I said a is set to be 0. That is my choice. But I'm showing you later on that if I choose a equals to 0, I'll be in trouble. Okay, so I'll substitute x equals to 3 into the expression here. Then I have tangent t and dt plus a constant. So this is a constant, and the whole thing must be equals to 5. So I have these conditions that my constant is just equal to 5 minus integrations of 0 to a and tangent t dt. So what is my constant? Right, the constant is a number which is 5 minus this thing. So this is an definite integral which I have to evaluate using tangent t, integrate t from 0 to 3. So that means in order to get the constant correct, I have to perform this integration that will run me into trouble. However, if I'm smarter a little bit in the beginning, instead of choosing a to be 0, but choose a to be 3, then my life will be much easier. If I choose a instead of 0, I choose it to be 3, which is allowed. Then I'll integrate the tangent t from 3 to 3, right? So according to the rule that we mentioned earlier on, if you have a functions that is like you have an t dt, you integrate from the same value of 3 to 3, it will always give you 0, right? This is one of the rule that we mentioned earlier on. So I would then change my choice of a from 0 to 3, then this term will just goes to 0 and my constant is just 5. So I am now in the correct position. The choice of my function f is just an integral function, which is made up of tangent t dt integrate from 3 to x plus a constant t. That will fulfill the condition that f evaluated at 3 is equals to 5. So that solves the problem. The question asks me for a function fx that fulfill two conditions. Derivative of it is tangent x, and the functions evaluated at 3 is just 5. So the answer for these questions is expressed in a form which is not as familiar to you, because the answer for your function is not an explicit function but an integral function, which is made up of tangent t integrate from 3 to x. But as I said, the integral function is just another function, but it's just a new form which you may have not encountered before, but it is still a valid function. Okay, the functions that is expressed in an integral form. So that finished our discussions on the questions example 4, right? So this is usually very typical question that you find in mathematics as well as in physics. That is, you want to find some expressions for an unknown function. You do not know what the function is, but you know some features of the function. Here you are asked to find some function f, which you do not know what it is, but you only know that the derivative of it is another function. So you know the derivative and you know the boundary condition of that function, but you do not know what function is. So you set up a scheme to obtain its expression. And again, here before I leave you, the choice of a equals to 3 and the constants equals to 5 are the two constants that would goes in your solution, right? So here you have an a and you have a constant. So I said a equals to 5, so a equals to 3 and constants equals to 5 would give you a solutions. But if I choose a to be 0, that means the constant will be some other number. Like you have to perform an integration to the tangent from 0 to 3 to obtain the integrations in order to determine the constant, right? So it's up to you, right? If you choose a to be some other number, which is not 3, you can still work out the values of the constants. It will still condition, the conditions will still fulfill for fx. So by no means the values of a and the constants are unique, right? Any other choice of the constants a and the constant value are still possible because they are still allows you to fulfill the condition. Right? So if you find a value which is different than your friends, it doesn't mean that your answer is wrong. It just simply means that both of you are using a different initial guess. But as long as your answer is consistent, then you are right. Now, before I leave these slides, just slightly, I want to mention this. Many of our students are very confident of themselves. They get some answer, but they sometimes are not sure, and they ask their friends and they check their answer against their friend, and then they ask if their friends' answer is the same as theirs, or the standard answer is the same as theirs. And then when they find the answer different than then they say, oh, I'm wrong. Then they start to think, why is that wrong? Sometimes this is not necessarily true because the answer could be wrong. The standard answer could be wrong. Our student is just not daring enough, not confident enough to think independently. They always want to seek assurance from a higher authority, thinking that the result or the answer from a higher authority is better than theirs. So this shows that our students are not really that well trained to seek knowledge independently. Okay, so try to be independent, try to think independently. If you're right, you're right, right? No matter what other people say. If your answer mathematically is very discrete, if it's right, then you're right. You show it's right. Sometimes I do stupid mistake and you find that I'm wrong. Why is that like that? You don't ask me why is it like that. Obviously, it's a mistake, right? So if you can prove it to be correct, then you would most probably not. But as long as your proof is correct. Okay, so then we have to go to a second part of the fundamental theorem of calculus that is called the evaluation theorem. Now this is a part that relates the definite integrals and the indefinite integral. So it says that if you have a function small fx, then you perform an definite integral for the function from a to b. That represents an definite integral, which gives you a value that represents the remaining sum of the function. And the values of it is just simply equals to the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So on the left hand side, we have an definite integral, which is the area under the function or the remaining sum, which is very difficult to calculate. Right? I've shown you for simple function, even fx equals to x. In order to calculate the remaining sum, you have to make the partitions, and then you have to calculate the convergence of a very complicated series in order to obtain the converged values of the remaining sum. So in general, calculating the remaining sum is cumbersome and could be quite complicated. But for a function that is continuous, then the calculations of the definite integrals could be highly simplified by evaluating the antiderivative of the small function f at values of b and a and take the difference. Right? So here you are translating the evaluations of the definite integral into evaluations of the single function capital F. Right? So which one is easier? Calculating the remaining sum is easier, or calculating the antiderivative is easier. Right? So here, if you are given some integrand and you are asked to obtain its definite integration from some a to b, then instead of calculating the integrations directly using the remaining sum, you just calculate what is the antiderivative. So tell me what is the antiderivative to the integrand. The integrand here is small f. So given a small f, think of the antiderivative. So if you can obtain or can get your antiderivative, then just evaluate your antiderivative at the lower limit and upper limit and take difference. So here, instead of carrying out an remaining sum, you just evaluate the antiderivative at the limits. So evaluating the values of a function is much easier than to evaluate the remaining sum. So the fundamental of term of calculus allows you to obtain the definite integral in terms of indefinite integrals evaluated at the limit value. So this is the gist of the fundamental theorems of calculus. When I was in Form 5, my teacher showed me this formula. He said, you just apply this, you'll be able to obtain the values of the integration. So when I do that, I just do it, right? Just, okay, this is the function. I just think of what is the inverse of it. Then I just carry out. And we have been doing this since, Form 5, Form 6, for many years, we have been doing this. But when you do that, when you evaluate the definite integral on the left-hand side, this one, you are actually applying the fundamental of theorem of calculus. So the fact that you can evaluate the left-hand side using the difference of the right-hand side is not straightforward, right? So it is actually proven, and people have gone through many intellectual arguments to arrive at these relationships that relates the integration to differentiation. Antiderivative is differentiation. The definite integrals or the Riemann sum is integration. So fundamental of theorem of calculus integrate or combine or sort of unify or relate the integration and the derivative of a function. So that is the evaluation of it. So there is a proof that you can easily read it for yourself. So according to the, wait for the slides to show. It's taking a lot of time to show the screen correctly. Okay, so you can easily get the proof of the second part of the fundamental of theorem of calculus very easily. That is, let me spend a little more time. So by definition, we have already proven this from the first part of the fundamental theorem of calculus. You define a functions, capital function fx, as an integral functions of the small function ft, then you prove that the capital function f is a derivative to the small function f. Okay, so then again, then you look at the definite integral of ft integrating from a to b. So from the previous theorem, again, specifically the additivity theorem, the additivity rules of definite integrals, it says if you have an integration from a to b, this is the same as integration from a to c plus c to b, where you just split the integration from a to b into two parts. You go from a to c and go from C to B. Right? It's just like you go from KL. So when you go to KL, you go to Ipoh, and then you go from Ipoh to KL. So the whole journey from Penang to KL is the same as you go from Penang to Ipoh and from Ipoh to KL. Right? It's just the same thing. So you just split the integrations of small ft from a to b into two parts, where you choose an intermediate values of c between a and b. Then you revert the limit of a and c with a negative sign. Then you have a common c here. You have a common c here, and by definitions, here you have the same constant. You have the same constant. So this is just your capital function f evaluated at b, and this expression is just your capital function f evaluated at a. Right? So this is just this statement is just equals to f at a with a minus sign. This expression by definitions is just the capital function f evaluated at b. And again, when we define the capital function f, we just choose an arbitrary constant. So you required this for this integration and this integration, the lower limit has to be common, have to be the same, in order to be able to express them with the same capital function f. So that will prove that the integrations of the integrand small f from a to b is just equals to the antiderivative capital F evaluated at b minus the antiderivative function capital F evaluated at a. So that is the proof of the fundamental theorem of calculus. So then it's quite easy now. You use this formula since secondary school. So a functions defined between a and b, and you're asked to perform its definite integral. What you need to do is that you just find out what is its antiderivative, what is its antiderivative, evaluate them at a and b, and sometimes the difference between capital F at b minus capital F at a is just written at f, and then you just have lower limit and upper limit. Or sometimes we just include this, like either way, but I prefer to use this notation to represent the difference between the capital function f evaluated at the upper limit minus the lower limit is a shorthand. This is example. You're asked to find the antiderivative. Well, you're asked to find the definite integrals of the function. So imagine this: you have 0 to pi. So the cos is a function that looks like this: 0 to pi. And if I ask you to find the definite integral of the cos 0, yeah. If I ask you to find the definite integrals, you are asked to find the area. And how do you find the area? In order to find the area, you have to know provide the summations of delta k. You sum the k from 1 to infinity, where you divide this f into a partition of x0, x1, blah blah blah, up to xn. Then you take the limit of n of k goes to infinity in order to work out this, right? So either you use theoretical evaluations to work out the definite integral by performing the remaining sum, or you use mathematical code, which I have shown you earlier on. The mathematical code can be easily used to calculate the remaining sum for a large n, but not n goes to infinity. So imagine this is the only way to calculate the definite integral, then you go crazy, right? You don't want to perform every time. If you want to find the definite integral, you calculate the remaining sum. But the fundamental calculus say, no, you don't need to. Just ask yourself, what is the antiderivative to the cos of x? Then evaluate them at the upper limit minus the values of it at the lower limit. That will do, right? So here, the functions that is in relations is this is cos t. The antiderivative to cos of x is then just equals to, sorry, I think here I better write it as x instead of t, just to avoid confusions. Okay, so here you have a small function f of x, which is equals to cos x. Then in order to calculate the integrations of cos x, then you just have to think what is the antiderivative to cos x. So the antiderivative to cos x is just minus sine x. Why is that so? Because f prime, sorry, with plus sign, not the minus sign. Because f prime of x will just give you cos x. So that is the only hint that you get to find out what the f is, the capital function of f is. Given this function, the antiderivative is this. Then in a sense, you have to memorize, because up to now, we only go from a function to its derivative, but we actually do not go from the antiderivative back to the function, right? So if I give you a function f, it's easy to get its derivative. But if I give a function ask it to get its antiderivative, it is usually much more difficult. So usually what we do is that you have a table that gives you a list of functions on the left, and the right hand side is the derivative of it. In order to check the antiderivative, you just look at the antiderivative part and then check back the inverse of it, that you get back the antiderivative. Well, anyway, we are going to discuss this in a minute. Usually you have a list of table that lists the function and its antiderivative, right? So this is obtained from another list, which lists a pair of function and its derivative, right? So when you reverse it, the derivative become the function, the original function become the antiderivative. Well, anyway, once you have found the antiderivative of the function, you can find sine x. No, I think there's something wrong with this. I think here this should be a positive sign instead of a negative sign. So there is a mistake here. I'm going to correct it later, but not now. Okay, so here I have very simple relationship that will give me the answer for the definite integral. So the definite integral for this is just equals to the antiderivative of cos x, which is sine evaluated at pi minus sine evaluated at 0. So this is just equals to sine of pi is what? Sine of pi is just 0, and sine of 0 is 0. So it's just, so answer is just equals to 0. No? Yes? No? I think it's not, right? So cos of 0 to pi, 0 to pi. Okay, so answer for this is the function from 0 to pi is, like, you start from here, you go to pi over 90, here. Yeah, so this is pi over 2, this is pi, this is 0, this is a function of cos x. So the integrations on the left hand side here is positive, and on the right hand side of pi over 2 is negative. So when you add up, then it gives you 0. Okay, so so that is a very simple illustrations of the applications of fundamental theorem of calculus. So you have the other part. So here you are asked to find what is the integrate the definite integration from minus pi over 4 to 0. So here you have a function fx which is secant x and tangent x. Then look at this small function f. Ask yourself, what is the antiderivative? That is, what is the antiderivative? How do you find the antiderivative? You have to think carefully. When you have a f, what is the capital function f such that when you differentiate it, you get back the small function f. So if you can remember it correctly, then the derivative of, I think, secant x, the derivative of secant x gives you tangent x, secant x, right? So from this relationship, then you know, the antiderivative to, sorry, that means here, when you remember this formula, that is the derivative of secant x give you tangent x, secant x, then it means the antiderivative to tangent x secant x is nothing but just the secant x. So the antiderivative to secant x tangent x is just secant x. So we have got this, then simply just substitute the values of this antiderivative. So this is just simply equals to the antiderivative, which is secant x evaluated at 0 minus secant x, where x here is pi over 4. Okay, so then you just work out what is the secant of 0 and the secant of minus pi over 4. So either you remember it from your memory or you press the calculator to calculate this. So I think secant x, I can't remember it, but secant 0 is 1 over cos 0. Then you have a cos of pi over 4, right? So just think of what is 1 over cos 0. 1 over cos 0 is 1 because cos 0 is 1. How about cos of pi over 4? So remember this, you have a CAST. So pi, negative pi over 4 is this angle. So in this angle, the cos of minus pi over 4 is positive. So cos of negative pi over 4 is the same as cos of pi over 4, because here negative pi over 4 is sitting in the fourth quadrant. So using this mnemonic, you know that cos of minus pi over 4 is just positive. So what is cos of pi over 4? Cos of pi over 4 is a cos of 45 degrees. Cos of 45 degrees is square root of 1 over 2. Okay, so then this is just equals to 1 over 1 over square root of 2, which is like this. So it will be just equals to 1 minus square root of 2. Okay, so that is what I think the answer is. So I'm not sure if this is true, but let us try to make a simple check. Okay, so I'm going to stop the recording for just a moment. Okay, so you look at this is a very simple mathematical code 5.4. So let me go and define my functions. Say this is example 5. Okay, so example 5 B. Okay, so example 5b is a function which I'm going to integrate. This refers to the secant of x and tangent of x. So the lower limit a is defined to be sorry, not here. The lower limit is defined. Let me take off this one. This is not relevant here. So the lower limit is negative pi over 4 and the upper limit is 0, and I'm going to integrate this. So just use Mathematica, is the n integrate. The Mathematica actually will allows you to integrate it quite easily. X from A to B. So let's see what we get. So there's a minus common sign here. So you press the calculator, you get a number which is minus 1 over this. So what I'm saying just now, a minute ago, I was saying, what was I saying? I was saying that the answer should be equal to 1 minus square root of 1.414. So I think I might be wrong. So just now when I calculate that, I said this is equal to 1 minus square root of 2, right? So that is what I'm saying. So I'm going to calculate this value exactly. This is my theoretical value which I calculated earlier on. So this is the theoretical value which I calculate using my iPad, and this is the number that is provided by Mathematica, and they agrees. So that means my answer is correct. So that is how you can use the Mathematica to perform a numerical integration to obtain the definite integrals. Now, other than that, you could actually also obtain the indefinite integral as well. So Mathematica is actually quite powerful. For example, if you have this, you can try to obtain the definite integral, right? So the definite integrals of a function of x with respect to x. Ask Mathematica, not, I think you call it integrate. Yeah. So you provide the form of the functions, ask it to integrate with respect to x, then it will give you the answer, right? The answer is secant x. So you can see the powerfulness of Mathematica. You provide the functions to it, then you can ask it to do definite integral or to perform the indefinite integral. The indefinite integral here is actually asking Mathematica to find the antiderivative. So this is amount to finding the derivative. Okay, so that is the example that I want to show you. So maybe now let me go back to the part example C. So let me open my part 4. So the part 4 which we are going to continue to talk about is example C. So let me go to example C. So here is example C. So okay, so this is wrong. I have to change this. Okay, so example C is the integration of this, right? So let me see what is the answer according to the Mathematica. Then I'm going to do this and then check it. Okay, so I think you can see my screen on Mathematica. So one side is okay. So now I just have to copy and paste. So I'm looking at the example 5C. Then I'll just define my functions for 5C to be 3 over 2 times square root SQRT square root of x minus 4 over x square. I think that is how you define the square. Yeah, I think so. X power true. So am I correct? Maybe not like this. Yeah, I think this is how you define the 4 square x square. Then the lower limit here is 1. Upper limit is 4. So let me find out what is the definite integrals, and let me do it one by one. Okay, so this is to find the definite integral. This is to find the indefinite integral, which is basically the the antiderivative, right? So let me execute this. Then now Mathematica has read in the expression of f. Then this will give you the antiderivative of the function without the constant. It should actually give you a constant, but for some reasons it doesn't give you a constant. But remind yourself that the antiderivative has a constant in it. So let me integrate this numerically. Is equals to 4. Right? So the answer for the integration is just equals to 4. You can easily look at this expression and convince yourself that f at 4 minus f at 1 is indeed equals to 4. So let me try to do this for you here. So let us evaluate the values of the function of f at 4. Here, this is 4. This is the expressions of 4 as well. Okay, so this is a term which is meant for f at 4. So I have to include this in a bracket. Okay, so this is the bracket that represents the capital function f evaluated at 4. Then it has to then minus, okay, I need a little bit of space. Where should I go? Okay, maybe I should make this slightly smaller in size, 20, maybe 24. Okay, so then I have to evaluate the values of the capital function at 1. So I have to replace the 1, 4 by 1, and then here we should be 1. Okay, so then you can evaluate this, and the answer should be equals to 4. So let's see what is this. So this is 4 raised to the power of 3. So this is 4 raised to the power of half. Then you cube it. Then this is 2 cube. 2 cube is then give you 8. Right? So this 8 is actually this number. Right? Is 4 raised to the power of 3 over 2 is 8. Then you have 4 times 4 raised to the power of 1, which is equals to 1. Right? So that is the value, which is equals to 7 minus the expression of 1 minus 4. Right? So then this should be just simply equals to, this is just 7 plus 3. 7 plus 3. 7 plus 3 is 10. So that means I am wrong. I am supposed to get the answer to be equals to 4. So let me check again. Is my function defined correctly? 3 over 2 raised to the power square root of x minus 4 over x squared. So I think I may have done some stupid mistake. I think here is minus. Okay, so this is a minus sign instead of a plus sign. Sorry, f is minus. Yeah, so it is plus. Okay, sorry, it's plus. So let me check again. This is 4 raised to power 3 over 2 plus 4 and 4 minus 1, 4, 1. So this is 8 plus 1. So 8 plus 1, 8 minus 1. So 8 plus 1. So this is not minus, this should be plus. So I'm sorry about that. So it should be 9. 9 plus 9 minus 1 plus 4. This should be plus 4. Okay. So it will be 5. So it will be 9 minus 5. 9 minus 5. 9 minus 5 is 4. Okay, am I correct? Yeah, 9 minus 5 is 4. So I got my answer to be agreeable with what given by Mathematica, which is 4. Right. So here I have finished demonstrated the applications of the antiderivative using the fundamental law of calculus. Then you can also obtain the derivative, the integration for the functions. Here you are asked what is the area of A and area of B. So area of A here, area of B. Now the first part of the question is indefinite integral of the functions. from 0 to 2 pi. So you can perform this integration. The integration is integrate the function of sine x from 0 to 2 pi. So I think the answer is the same as similar to this one. So you can easily obtain the integrations of the function. Maybe I can write it here if I think it should be possible. The answer should be just 0. Okay, so let me try to get the answer done. Okay, so I'm going to integrate the functions. Okay, maybe I should just use this integration sign for the functions of sine x, the x, and the x is to be integrated from 0 to 2 pi. So that would give me the answer. So I have to evaluate the antiderivative of the function at 0 minus the antiderivative of the function at 2 pi. 2 pi. Okay, let me drag it a little bit to express myself better. I need a little bit of space. Okay, so then this is just equals to the antiderivative. So the antiderivative of sine is actually cos x, but actually it's not cos x, it's minus cos x. So you have to evaluate the cos x at the values of 0. So I need a bracket to evaluate the difference between them. So usually I would look for these expressions. Okay, so you have a minus cos x evaluated at 0, and then minus the antiderivative evaluated at 2 pi, right? So this is equals to 2 pi. And then you have a minus sign, which is coming from the antiderivative. So you have a minus, then you have a plus sign here. So I have to have then a plus sign. Right? So that would be the way how I'm going to evaluate it. So I need to show this to be just equal to, so this is to evaluate the cos at 0, right? So just substitute x at 0 for this expression. So I'm just going to substitute x equals to 0 plus this, I'm going to replace it by cos of 2 pi. 2 pi, that would be like this. Okay. So what is the answer? The answer is just equals to a simple value. Cos of 0 is minus 1 plus cos of 2 pi. Cos of 2 pi is just cos 0, right? It's the same circle, right? You come back to a circle, then you get 1 as well. So you got 0, right? So straightforwardly, the integrations from 0 to 2 pi for sine x is 0. And then this is for the part B or part A of the function, part A of the questions. So if you want to calculate the area of axis from area to here, the area is to be integrated from 0 to pi. So for B, the area for the axis between the graph of an axis over 2 pi. So you have the area which is in the positive side and the area of the negative side. The area is an positive value, right? Area is like the area. You cannot have negative area. So if you want to calculate the area, you have to integrate the sign from 0 to pi. Then you can evaluate that quite easily. To calculate the area in this side, you just have to integrate from pi to 2 pi, and the answer that you comes out will be a negative number. Then you just have to revert the negative number into a positive one. It would show to you that if you perform this integration from 0 to pi for sine, you get 2. That is the values of the area in this blue region. For this region, which is shaded with this color, I didn't know what you call it. Call it pink, or no, you call it orange, or you call it purple, whatever you call it. magenta. No, I think this is just a some color. Then when you integrate from pi to 2 pi for sine x, you get a negative number, which is -2. So -2 is the integration from pi to 2 pi, but the area is the negative, if it's a positive number. So you just have the absolute values of the integration to get 2. Okay, so I'm not going to show this, but anyway, when you are asked for the area, your answer should be reported with a positive value. Okay, so you know that for this function, from 0 to 2 pi, the function is positive. From pi to 2 pi, the function is negative. So when you integrate in the negative area, from pi to 2 pi, the integrations is the negative of the area, because the integration is a negative number. So you always remember to revert the integration if it's negative to represent the area. This is another example, which is slightly more complicated. It says you have a function that looks like this, and you're asked to find the area. So the area that you are going to find is this. So you are going to find this area and find this area. Now, in order to find the area, you have to know where are the functions positive, where are the function that is negative. So to find the function, first of all, you have to find the values of 0. That is, you have to find the point of the function where it cuts the x-axis. So you can easily factorize the polynomial of degree 3. Sometimes I call this order 3. We got confused, but when I say degree 3, order 3, I mean the polynomial of power 3 or equal. Then you just factorize it. Then you can easily factorize it to be like this. So you can easily see that the zeros of the function occurs at x equals to 0, x equals to -1, and x equals to 2. So that is the x equals to 0, x equals to -1, and x equals to 2. So you have 3 zeros, then you sketch the functions. Then easily you can see from the sketch that the area of the function is divided into 2 sections. From -1 to 0, the area is positive. The function is positive, therefore the area is also positive. For x between 0 and 2, the function is negative. So in order to obtain the area in this shaded area, you just have to integrate it from 0 to 2, then you have to revert it. So maybe I showed you here, since I think it's possible to do it here without much difficulty. So maybe let me insert and let me insert a text box. So insert a text box. Okay, so I'm going to write my text box here. Okay, so in the text box, I'm going to insert my function is x cubed minus x squared minus 2x, right? So this is the original function, and I'm going to integrate this. So I need the integration sign to show my integrations, and it's going to integrate with respect to x. So here is my integrations. The integrand is x cubed minus x minus 2x, and in order to obtain the integrations from 0 to 2, I'm not going to show the integration of -1 to 0, but I'm going to show only from 0 to 2. So you start off from 0 to 2. So this will represent the integrations for the functions in the region of 0 to 2. But this is just the integration. As I mentioned, the integration could be positive, could be negative. The definite integral could be positive, negative. But if you want to find the area, then the area must be the absolute values of the integration. So just have simply calculate this. It's quite straightforward. So it just equals to the antiderivative of the functions. So you have to just figure out what is the antiderivative for this function. So the antiderivative of the function could be done quite easily. Let me do it one by one. So the first antiderivative here would be the antiderivative of x cubed. The antiderivative of x cubed is x power 4 over 4. So this is the antiderivative to x cubed, because d dx of x power 4 divided by 4 give you x power 3. Then you have another term, which is the antiderivative for x squared. The antiderivative of x squared is just 1/3 of x cubed, right? So 1/3 of x cubed will give you when you take the derivative of it, give you x squared. Then the antiderivative of minus 2x is just simply equals to x raised to the power 2. So that is how you obtain the antiderivative. Then you evaluate the antiderivative at three different at the upper and lower limit. So this is my antiderivative, and I'm going to evaluate it at the lower limit and upper limit, which is 0 and at 2 as well. Okay, so just have to calculate this one by one. I'm not going to try to do it for you, or maybe you should do it for yourself. So just have to do this. Okay, I'll just do it here, and since I already done it halfway. So it's going to be the values, which is to be evaluated at x equals to 0 and 2. So let me write it here. Okay, maybe I should just cut and paste and put it here. It's easier that way. Okay, so then the calculations will just proceed as this. So it would be maybe I make it larger. Okay, so this would be just equals to this one minus this. Yeah, okay, so I think I'm almost done. So this is to evaluate at 2. Okay, so let me see what is the values of these functions. The values of this function is just equals to 0. So this term will become 0, 0, 0. So the term here will be just 0. This 0 refers to evaluating the polynomial at 0, right? Then you have minus something. That something is just equals to the expressions given by this. So it is a function that includes everything. So to make things more clear, I would like to enclose it in a bracket. Okay, to show that it is a minus sign there. So be careful of the minus sign though. So now I'm going down here, and then I have a minus sign of this whole bracket. This whole bracket, we're going to reproduce it here. So it's going to be evaluated at x equals to 2. So this will be equals to values of 2, 2, and then this will be equals to 2, and this will be equals to 2 as well. Okay, so that is how I evaluate the functions at 2. Okay, so that is how I do it. Then you can just continue and see for yourself how it looks like. So this will be a minus sign. So I'm going to take off the minus sign and it become positive. This is a minus sign. Then this is a positive sign. Then this is a positive sign. This is equals to 4. This is equals to 8 over 3. 8 over 3. Then this is equals to 16. 16 divided by 4. This is equals to 4. So easily obtained to be just a value which is just equals to 8 over 3. But it has to have a minus sign, I think. So where is my minus sign? Let me see. I think must have done some mistake somewhere. There must be a minus sign that I have been missing, because the values for the functions from 0 to 2 is minus. So I must have missed my minus sign somewhere. So this is equal to 2. Okay, I think I made a stupid mistake. That is, I have to evaluate the difference between the upper limit and the lower limit. So this should be the evaluate at the upper limit first, then only at the lower limit. So I have to revert this. It should be 0. So I think that is a more appropriate way. So then this will be just equals to 0. So, and then here is a minus sign. So I think that should be the way how it is done, minus 0. So there's no minus sign. So there's no minus sign here. So this is plus, and this is a minus, and this is a minus sign. Okay. So I give you a minus. So I'm showing you all the single steps of how you evaluate the definite integral, the indefinite integral or antiderivative at the upper and lower limit. That is how you do it. My teacher showed me this when I was in Form 5, and I'm going to show you again. So I'm just trying to show you step by step how you actually evaluate the antiderivative, so that you have no reason to say no, you don't know how to do this. Okay, so that will give you the integrations, but the area of the functions is not like that. The area is, so this is the integrations of the function from 2 over 3. That is a minus sign. So let me write it here. So this is a function that I'm integrating f of fx, and it is a value which is minus sign. So the area should be then just simply equals to, let me cut and paste the text box. So the area between x equals to 2 and x equals to 0 and 2 is the absolute values of the integrations, definite integrations should be equals to the absolute value, which is just the absolute value of minus 8 over 3, and it must be 8 over 3, right? So hope that you understand what I mean here. So you can perform the integrations from 0 to 2, and if it is asked for an area, then the area must be positive. So you have to put an absolute sign to throw away the minus sign. If you're only asked for calculating the integrations or the definite integration, then you just leave the answer. So before we end this slide, just a reminder, you have to be careful what the question is asking. If the question is asking for the integration, then you just perform the integration as it is. Like this is performing integration for x from A to B. But if you're asked to calculate the area, then you have to make sure that the area have to be put in the absolute sign, and you have to make sure that when you perform the integration, the functions that you are integrating must have all the function to have the same sign. So here, you cannot mix the integration from -1 to 0 with the integration from 0 to 2, or else the area in the positive side will cancel off with the area in the negative side. So when you are asked for the area, you have to integrate function piece by piece, and when you integrate the function in that piece, the function has to be of the same sign. So here, negative sign between 0 and 2, here is positive sign. So you have to separately integrate the function in different regions of x, so that you can obtain the area properly. Okay, so that's all for the lecture for this topic. We're going to stop our recording now. Okay.